In the last lesson, we studied the physics of fluids at rest, the field we call hydrostatics. We discussed how fluid pressure gets exerted equally in all directions at a given point in a fluid. We discussed how the force on a surface due to fluid pressure must act perpendicular to the surface. We discussed how the pressure in a fluid increases linearly with fluid depth. We discussed how changes in pressure to a confined fluid get transmitted throughout the fluid, what we call Pascal's principle. And finally, we discussed the upward force acting on objects immersed in fluids at rest, called a buoyant force, and how to calculate buoyant forces using Archimedes' principle. But now we want to ask the question, what happens when objects are immersed in fluids that are moving? This is the branch of fluid mechanics we call hydrodynamics. As you'll soon see in this lesson, some rather interesting and unexpected physics comes into play when fluids are in motion. Let's take a look.
Have you ever seen the love between a ping pong ball and an airstream? We're going to use this air source to demonstrate the attraction that a ping pong ball will have for a moving stream of air. This air source will blow out air. I'm going to place the ping pong ball in the air source, and you'll notice that even as that air stream moves to the right and to the left, that ping pong ball will remain attracted or fixed in that stream of air. We can explain this using Bernoulli's principle, which we'll talk about shortly. But first, let's demonstrate this.
So in thinking about the demonstration that you just saw, when the air source was in a vertical position, perhaps it wouldn't surprise you that the ping pong ball remained afloat. You might reason that the upward force of air was opposing the downward force of gravity. But what about when the air source was held at an angle? How can you explain the fact that the ball remained there at rest rather than accelerate? So let's take a look at a free body diagram. In this case, you can see that clearly there's a downward force of gravity acting on a ball, and there's the force of the airstream acting on it at an angle. But is that ping pong ball disobeying the great master himself, Isaac Newton? Clearly, there must be another force that we're not accounting for if the ping pong ball is to remain suspended at rest in a state of mechanical equilibrium. We'd better figure out what this unknown force is, or you can kiss goodbye everything you learned about Newton's second law. So we'll begin our investigation into this unknown force by taking a look at two different types of fluid flow. The first type of fluid flow is what we call streamline or laminar flow. The second type is what we call turbulent flow. Let's take a look at the characteristics of each of these types of fluid flow so that we can distinguish between them. Starting with streamline or laminar flow, okay, the illustration I'm showing you over here on the right shows you various streamlines. And a streamline, okay, I'll trace out one of these streamlines. A streamline is simply the path that a layer, or let's say small sample of fluid, will take, okay, in its motion. You can see here that adjacent streamlines, that is adjacent layers of fluid, slide smoothly past each other. These streamlines never cross, and that's characteristic of laminar flow. You'll never see streamlines crossing each other because, okay, different layers or pieces of fluid slide smoothly past one another. You can also say that for streamline or laminar flow, if we look at a particular point in the fluid, okay, like where my laser pointer is right now, we can say that the fluid speed and direction or fluid velocity at that point remains constant in time. Let's contrast this with turbulent flow. It turns out, okay, that above some critical speed, okay, the fluid flow will become turbulent. And you can see here what happens in this pipe, okay, that the flow starts out in a streamline or laminar fashion where these streamlines are not crossing each other. But due to the constriction here, which as we'll see will cause the fluid speed to increase, okay, in this region over here, these layers of fluid no longer slide smoothly past one another. Okay, you get eddies or these little whirlpools, okay, to form. I'm going to show you in the simulation here. Okay, you can see that for streamline or laminar flow here, this is a nice simulation because these different colors represent the streamlines of your moving fluid, and you can see that the layers of fluid don't actually cross each other, okay, as the fluid moves from left to right. Okay, as opposed to in the case of turbulent flow here, okay, you can see here that, okay, the fluid layers or streamlines are crossing each other. Okay, they're not sliding smoothly past each other. I thought this was going to be a give us changes in time, but I guess I was wrong on that. Now that we've talked about the difference between streamline or laminar flow and turbulent flow, we're now in a position to define what we mean by an ideal fluid. Because the rest of this unit, we're going to be talking about the physics of ideal fluids. So when we talk about an ideal fluid, the fluid flow is laminar or streamline. This is not to say that we can't talk about the physics of turbulent flow, okay, but that's not what we're going to be talking about in this unit. This is certainly a topic that has been studied. It's certainly a much more complicated topic, but when we talk about resonance later on this semester, okay, we may briefly discuss this theory of vortex shedding, which does apply to turbulent fluid flow. For now, though, we're going to consider the fluid flow to be laminar. Okay, we also assume that the fluid is non-viscous, in which case there's no frictional forces between fluid layers. As those fluid layers slide smoothly past each other, we're talking about very smoothly, so that there is no internal frictional forces between adjacent layers. We also assume the fluid is incompressible. Okay, that means the density of the fluid remains constant. So obviously this is the case for liquids. It is not the case for gases. So when we want to apply the physics of ideal fluids, what we're going to be talking about in this unit, to gases, we can do it, okay, but our answers become only approximations. Okay, the physics starts to break down when the density of the fluid changes in time. And finally, we would say that fluid flow is irrotational. That if you look at any little piece of a fluid, that any little piece of a fluid, as it moves, it has no angular momentum about any point. Okay, and you can imagine when we talked about eddies forming, okay, these little whirlpools, that clearly represents rotational fluid flow. When you look at streamlines, however, we see that a streamline moves. Now, it may move in a curved fashion, okay, but there is no actual full rotation, okay, to the motion of any little piece or segment of fluid. To describe moving fluids, that is fluids in motion, we need to discuss the concept of flow rate. The flow rate measures how much fluid flows as well as how fast it flows. When it comes to how much fluid flows in a pipe or canal or whatever, we can measure the amount of fluid that flows by measuring either its mass or its volume. Therefore, we have two ways to calculate flow rate, one in terms of mass, the other in terms of volume. So let's consider a fluid that is moving through a pipe of varying cross-sectional area. And if you look over here in the left-hand portion of the pipe, okay, the cross-sectional area starts out rather large, having a value of A1, but by the time the fluid has reached the right-hand portion of the pipe, where it's constricted a bit, the cross-sectional area has decreased to a value of A2. We'll use a symbol Q, capital Q, to represent flow rate, and V for volume. So the volume flow rate can be defined as follows. It's the volume of fluid that passes a given point in the pipe per unit time, delta T. So to come up with an expression for the volume flow rate at point 1 over here, we need to figure out what volume of fluid, okay, passes point 1 in a given time, delta T1. Well, as you can see here, the volume of fluid passing that point in a given time is simply the cross-sectional area, okay, times delta L1, okay, this distance here, okay, so that cross-sectional area times delta L1 gives us a measure of volume. And when we look at delta L1 over delta T1, if we're talking about a piece of fluid moving a distance L1, delta L1 in a time delta T1, that is simply a measure of the fluid speed at that point. So this expression here, A1V1, that is a cross-sectional area, okay, at this point in the pipe here, times the fluid speed at that point in the pipe, that gives you a measure of the volume of fluid passing that point per time. We can similarly talk about the mass flow rate. Once again, symbol capital Q for flow rate, M for mass. By definition, the mass flow rate is simply the mass of fluid that passes a given point in the pipe per unit time. So if we want to find what is the mass flow rate at point 1, okay, we're talking about delta M1, that is a mass of fluid passing point 1 in a given time, delta T1. And remember that the mass of a fluid is related to the volume of the fluid by this concept of density. So rho 1 times, okay, the volume, okay, that passes point 1 divided by delta T1. And once again, delta V1 over delta T1 from above is simply, okay, A1, okay, times V1. So we see that these flow rates are pretty similar, okay, but when we talk about the mass flow rate, it's measured by the density times the cross-sectional area times the fluid speed at that point in the pipe. So now that we've talked about the concept of flow rate, we can state the equation of continuity as it applies to fluids. So when we talk about fluids, we'll start out with a very general statement that applies to all fluids, and we can say that the mass flow rate is constant. To apply this in a problem-solving environment, a more useful formula would be to say the mass flow rate at one point in your moving fluid must be equal to the mass flow rate at a second point in the moving fluid. And since we have an expression for the mass flow rate, we can then say that, okay, the mass flow rate at point 1 given by rho 1 A1 V1 must be equal to the mass flow rate at point 2 given by rho 2 A2 V2. I say this applies to all fluids, okay, whether the fluids are compressible or incompressible. So basically, this applies to both liquids and gases. And if you're solving a problem involving gases, then this is the expression for the equation of continuity that you would need to use. Now, in the special case of incompressible fluids, where the density is constant, and remember, this is not a good approximation for gases, but it is a good approximation for liquids. For that special case, we can then take it a step further and say that the volume flow rate is constant, which we can say as Okay, the volume flow rate at one point in the pipe must be equal to the volume flow rate at a second point in the pipe, or A1V1 must equal A2V2. What is the physical justification for the equation of continuity? Okay, the equation of continuity is nothing more than a statement of the law of conservation of mass as it applies to fluid flow. If you think about it, if the continuity equation was not true, then the mass of a fluid flowing through a given cross-section per unit time would not be constant, implying that mass would not be conserved, that there could be sources or sinks in your moving fluid, that mass could either be created or destroyed as the fluid moves. And we know that this cannot be the case. So we'll look at a few examples to see what the continuity equation tells us about the nature of fluid flow. We'll look at a couple of qualitative problems as well as a quantitative example. So in the first example, it says river varying width. What happens to the water speed when the river narrows? Well, you don't have to take a physics class to know this, okay, but let's see how the continuity equation predicts, okay, the result here. So we say that if the volume flow rate is constant, okay, and if we're talking about a liquid, we can use the volume flow rate as opposed to the mass flow rate. If the volume flow rate is constant in time, this tells you that as the cross-sectional area gets smaller, as the river narrows, then the fluid speed must get bigger, that there is this inverse relationship between the cross-sectional area and the fluid speed, okay, in order for the flow rate to remain constant. So like I say, this applies to pipes, rivers. You know that when a river narrows, okay, that's where your rapids are going to be. That's where the speed of the water is going to be the greatest. The adjustable shower head. How is the speed of water coming from the holes in the shower head controlled? Okay, it's a simple matter of cross-sectional area. So you can see here that by decreasing the cross-sectional area of the holes, that is the total cross-sectional area of the holes, the speed of the water leaving the holes will increase. So you know that in your adjustable shower head, if you want to put it on the massage setting where you have a high fluid speed, you're going to have a far fewer number of holes so that the total cross-sectional area of the water coming out of those holes will go down. Let's take a look at a quantitative example here. So arteriosclerosis, we're told that blood normally flows with an average speed of about 10 centimeters per second in the large arteries, okay, having a radii of about 0.3 centimeters. Okay, suppose that a small section of an artery is reduced in radius by 1/2 because of a thickening of its walls. Okay, calculate the blood speed past the constriction. So as the simulation shows you here, okay, looks like we've got some arterial plaques building on those walls, which are going to decrease the cross-sectional area. And here we're told that the radius decreases by 1/2. Okay, what's going to happen to the speed of the blood in that region of the artery? So once again, we're dealing with a liquid, so we can use the equation of continuity expressed in terms of volume flow rate. And here, okay, if we think of a circular cross section, then we'll use the area of the circle being pi r squared. And when we plug in the numbers here, okay, the pi's will cancel out on both sides of that equation, okay, but we're told that if the radius of the healthy portion of the artery is 0.3 centimeters on the left, okay, and that radius gets reduced by a factor of 1/2 here on the right, okay, it'll be 1/2 of 0.3, and don't forget to square it. We know that in the healthy region, the fluid speed is 10 centimeters per second, so what happens here when we solve for V2 in the constricted region of the artery. And when we do this, we get a speed of 40 centimeters per second. So you can see here, the danger with arterial constriction, I should say, that the radius decreases by a factor of 2, but the fluid speed increases by a factor of 2 squared, or 4. We'll see later on when we talk about Bernoulli's principle why this is so problematic for blood flow in the arteries. So this brings us to Bernoulli's principle, a very important physical principle that tells us the relationship between fluid speed and fluid pressure for the case of moving fluids. Later in this presentation, we'll see that Bernoulli's principle is nothing more than a statement of the law of conservation of work and energy applied to the case of fluids. We'll start by looking at Bernoulli's principle in a qualitative fashion to explain many naturally occurring phenomena. Then we'll derive the Bernoulli equation that will allow us to obtain quantitative information about phenomena. So Bernoulli's principle can be stated in a qualitative way as follows. Where the velocity of a fluid is high, the fluid pressure is low, and where the velocity of a fluid is low, the fluid pressure is high. In other words, there is this inverse relationship between fluid speed and fluid pressure in a given region where a fluid is in motion.
We're going to take another look at a very cool demonstration involving Bernoulli's principle and a ping pong ball. What I have here is a funnel attached to the end of this tube, which is attached to a source of air. And this source of air, well, blows air out from the funnel. We turn it on here, and you'll see when I hold this piece of paper, okay, that air is being blown out from this funnel. What I'm now going to do is take a ping pong ball and I'm going to put it at the base of the funnel when I hold it vertically. Let's take a look at what happens. Even though air is being blown out from the stem of the funnel, that ping pong ball is not being forced downwards in the direction of gravity.
So to try to explain why this ping pong ball remains in the funnel when air is blowing it in the direction of gravity, let's take a look at a few of the streamlines surrounding the ball. What you can clearly see by the white streamlines in the illustration is that in the region above the ball, the air is moving quite fast there. In other words, we have a high fluid speed and according to Bernoulli's principle should have a low fluid pressure. Notice in the region below the ball, there's not a lot of moving air in that region. In that case, we have a low fluid speed and a much higher fluid pressure. So you can see here that this pressure gradient, okay, the fact that we have a higher pressure, fluid pressure below the ball than above, translates into a pressure gradient. And since you know that pressure is directly proportional to force, that provides us with this net upward force that keeps the ball in equilibrium in the funnel.
Now this one I call blowing between the sheets. And this is something you can do at home if you've got a couple pieces of paper. Okay, hold two pieces of paper in each hand and blow right between them. And notice what happens. The pieces of paper come together. If you only have one sheet of paper handy, well, you can do a similar demonstration, have just as much fun. Okay, take a piece of paper and blow right across the top surface of the paper and notice what happens. Okay, we can get that piece of paper to rise. Let me do it from a side view here. We can get that piece of paper to rise right up against the force of gravity. To explain this, we need to know a little bit about Bernoulli's principle.
All right, so let's see how Bernoulli's principle can once again be used to explain this demonstration. Believe it or not, hopefully you'll start to see the pattern and see how similar, okay, the explanation is for this demonstration as for the case of the ping pong ball in the funnel. So we start here. This is a side view of a sheet of paper. We'll simply look at the single sheet of paper, okay, and see what makes that paper rise. And here is our airstream. You'll notice these green streamlines, okay, suggesting moving air above the piece of paper. And you'll notice that when we have the air blowing above the piece of paper, okay, it causes it to rise up. How would we explain this? Well, we can clearly see that above the piece of paper, this is a region where the fluid speed is high and therefore the fluid pressure is low. Compared to the region below the paper where we have very little moving air, okay, that's a region where the fluid speed is low, and according to Bernoulli's principle, the fluid pressure should be high. So once again, we have this pressure gradient set up across our piece of paper, and a pressure gradient, that is a pressure difference, translates into a net force. In this case, a net upward force that makes this piece of paper rise.
So we're going to take a look at the physics behind an atomizer, like a perfume atomizer. Have you ever wondered how a perfume atomizer is able to shoot perfume out of a bottle that is not pressurized? Okay, well, the atomizer makes use of Bernoulli's principle. But rather than shooting perfume out of our atomizer, we're going to shoot Rice Krispies so we can actually see the effect. Now, the operation of an atomizer, I'm going to take this tube here, and all I'm going to do is I'm going to blow air across the top of the tube. According to Bernoulli's principle, if I look at the air that's moving over the top of the tube, it's moving quite fast. And where the air speed is high, the air pressure in that region is low. Down here where the Rice Krispies are, there's very little moving air. The airspeed is low, and therefore the pressure is high. Because we have a difference in pressure between the bottom of the tube and the top of the tube, okay, the air and the Rice Krispies are going to move from the low pressure region to the high pressure region. So let's see Bernoulli's principle in action and see how the atomizer works. Take my air source, I'm simply going to blow air across the top surface of that tube.
All right, so let's use Bernoulli's principle to try to explain the physics behind the atomizer. So here we have our cup full of Rice Krispies and our vertical tube, and here we have an air source. Okay, you see the pink streamlines above the tube, where we can assume that we have a high fluid speed, okay, and according to Bernoulli's principle, therefore a low fluid pressure. Notice that in the region where the Rice Krispies are, there's not much moving air there, so that's a region representing a low fluid speed and therefore a higher fluid pressure. Once again, a pressure gradient gets set up across our tube, which translates into a net force, okay, that causes these Rice Krispies to, okay, move from the high pressure side to the low pressure side. So in this slide, we'll see how Bernoulli's principle can be used to explain the very nature of flight. Now, I want to be really clear that if you look at that big old jet airliner, that 747, and you're wondering how is it that a fully loaded massive airplane like that can get off the ground? Well, Bernoulli's principle does come into play, but Bernoulli's principle alone could never explain how a fully loaded large aircraft is going to get off the ground. It has more to do with Newton's third law. But let's take a look at the Bernoulli effect. And I will say it comes into play much more when we talk about, let's say, fighter planes, which can move quite fast, okay, and are much less massive. So in order to see the Bernoulli effect, we need to take a look at a cross-section of an airplane wing, okay, or a bird wing. And we see that it has this characteristic shape. It is not flat. Okay, so the curvature of the wing forces the air moving above the wing to travel a greater distance over the wing, okay, in a given time period, thus making the air moving above the wing travel faster than the air moving below the wing. So you can see here in this diagram that these air streams, okay, would then suggest that there's going to be this pressure gradient. So let me show you in this cross section of the wing here that I can control a little bit better. I'm showing you some of the air streams in blue. You can clearly see that the air traveling above the wing travels a greater distance, okay, in the same time, meaning it travels faster. So the fluid speed above the wing is high, okay, generating a low pressure region, okay, whereas below the wing where the air is traveling slower, okay, the fluid speed is less, meaning the fluid pressure there is higher. Once again, we see that this pressure gradient, okay, translates into a net upward force that we call a lift force on the wing.
So we're going to take a look at the physics behind the curveball, sometimes called the Magnus effect, which is really just a phenomenon of Bernoulli's principle. When we talk about the curveball, what we have is we have a ball which is moving through the air, and in addition to the forward motion of the ball is given a spin. Okay, and as we'll see, because of that spin and its forward motion, a low pressure region develops which causes a sideways or deflecting force on the ball, which makes the ball curve, so to speak. Now, because we cannot slow down the motion of this ball, we're going to use this apparatus right here to simulate the curveball. With this apparatus here, rather than throwing it through the air, what we're going to do is we're going to take a source of air and force the air past this vertical cylinder. That is going to simulate the forward motion of the ball. To get the spin, I'm going to pull on this cord and I'm going to cause this thing to rotate. So this cylinder is going to have rotational motion, it's going to spin, in addition to having air moving past it. And what we're going to see is that there's going to be a sideways or deflecting force on it, which is going to make it move to the side. In the same way, we have that deflecting force on the baseball that causes it to curve. So let's get this going here. I'm going to pull on the string to cause the spin. Okay, let's activate the air source here. Notice when I blow that source of air, okay, it causes it to move to the side. The simulated curveball, folks.
Now, let's see how Bernoulli's principle can be used to explain the physics behind the curveball, sometimes known as the Magnus effect. What you see here is the baseball with its seams, and in this picture we're looking at a top-down view, let's say an airplane view of the ball. The curveball happens because the ball is made to spin in addition to moving forward. So in this picture here you see the velocity vector representing the motion of the ball forward, but you also see the red arrows suggesting the direction of the ball's spin. Now, from the point of view of the ball, we can show the streamlines. We can see the air that is moving past the ball as it travels. And what we're going to do is we're going to take a look at the effect of the spin. That spin causes a boundary layer of air in contact with the seams of the ball to move more rapidly on one side of the ball than the other. So let's look at a point on really the left-hand side of the ball, which is on the top part of your computer screen, as compared to the point on the right side of the ball, which is really on the bottom portion of your computer screen. We'll look at these 2 points. Now we really have 2 velocity effects. The first is due to the forward motion of the ball. And from the point of view of the ball, we can say that the air is rushing past it, as you see with these 2 velocity vectors. But in addition to the forward motion of the ball, we have the spin of the ball. And when we represent those velocity vectors, we see that on the left-hand side of the ball, that's the upper portion of your computer screen, because of the direction of the spin, the air actually is moving opposite the air due to the forward motion of the ball. On the right-hand side of the ball, that is the bottom portion of your screen, you see that the air there is moving in the same direction as the air due to the forward motion of the ball. So what happens there is that we have, when we look at the vector sum, on the left-hand portion of the ball, that is the top portion of the computer screen, we see that the spin effect cancels out some of the forward motion effect, giving us a smaller air velocity there. On the right-hand side of the ball, the bottom portion, in that case, the moving air due to the spin goes to reinforce the forward motion of the ball. Those velocity vectors are in the same direction, giving us a larger air speed there. So what we get then is that on the left-hand side of the ball, that's the top portion, we have a lower fluid speed, lower air speed, and consequently a higher fluid pressure. On the right-hand side of the ball, the bottom portion of your computer screen, we have a higher fluid speed and therefore a lower fluid pressure. This causes a pressure gradient to exist across the ball, and that pressure gradient in the language of force gives us a deflecting force acting on the ball, as shown with the green arrow. So that in addition to the ball moving forward, that deflecting force causes the ball to curve. Bernoulli's principle can be used to explain the very survival of underground mammal dwellers like gophers and moles. As you see here in the diagram, in this case we're taking a look at prairie dogs. They construct their burrows with openings at different elevations. Notice that these underground mammal dwellers do not have a single opening. They have multiple openings. And by constructing their openings at different elevations, chances are that airspeed will differ because it's a function of elevation. And this difference in airspeed between a hole that is higher up and a hole that is lower down will create a pressure difference across the openings in accordance with Bernoulli's principle. This allows air to flow from the region of high pressure to low pressure and allows air to circulate in the burrows. Bernoulli's principle can be used to explain housing design as well as problems that houses encounter in high wind areas, such as areas that are hurricanes. Why are rooftops inclined to pop off rather than blow off in a hurricane? As we'll see, when you see pictures of hurricanes that have hit certain areas, and when houses end up losing their roofs, a common misconception is that the sheer force of the wind blows these roofs off the houses. But as we'll soon find out, it's really not the force of the wind that blows the roof off the house. It's really a difference in pressure that causes the roofs to pop off of a house. So to see this phenomenon, we'll start by taking a look at airflow on the top surface of the roof during a hurricane. Notice that if the doors and windows are closed, there is very little airflow inside the house, but with high wind speeds, we have a great deal of airflow and high wind speeds on the roof of the house. The differences in airspeed between the inside and the outside of the house cause a pressure gradient to develop. And as we see, according to Bernoulli's principle, the high fluid speed on the top of the roof on the outside causes a low fluid pressure there. And inside the house, where there's very little moving fluid, we have a low fluid speed and a high fluid pressure, causing a fluid pressure difference, a net force causing the roof to pop off. So that might lead us to ask the question, what would you think would be the ideal design for a rooftop in a hurricane area? Well, as you see in the picture here, the peaked roof acts like the top surface of an airplane wing. It actually causes a greater fluid speed. A flat roof is advantageous because we would have a lower speed on the surface of a flat roof than a curved or pointed roof.
So have you ever noticed when taking a shower in a stall with a shower curtain as opposed to a glass door per se, that very often when you turn the water on in the shower, that shower curtain gets drawn up to your body? Okay, you have a sticky shower curtain. Well, this can be explained very simply using Bernoulli's principle. That in the region inside of the shower where you have a moving fluid, okay, that is water, where the water speed is high, okay, this creates a low pressure region on the inside of the shower compared to a higher pressure region outside of the shower where there is no moving fluid, no moving water. And of course, this difference in pressure, this pressure gradient, can result in a net inward force. So we're going to use Janet Leigh here in the Alfred Hitchcock thriller Psycho of 1960 to illustrate this. Okay, you will notice that when she turns on the water, okay, that high fluid speed causes a net inward force, okay, that causes the inward motion of the shower curtain. So we see that Bernoulli's principle can be used to explain a very common cause of heart attacks due to arterial blockage. So what I'm showing you in the diagram here of the artery is you will see this arterial plaque which is attached to the arterial wall. And you'll notice that because of the formation of that arterial plaque, it causes a constricted region in the artery, okay, where the cross-sectional area has been reduced. And according to the equation of continuity for fluids, okay, this constriction, okay, this reduced cross-sectional area should lead to a higher fluid speed, higher blood speed in that region of the artery. So we notice that, okay, in this region above the plaque here, right near the arterial wall, there's very little moving fluid, very little moving blood there, okay, which would suggest that the blood pressure there should be higher than in this constricted region below the arterial plaque, okay, where the blood speed should be high, okay, creating a lower blood pressure there. So once again, as we see, okay, this pressure gradient, this pressure difference, okay, set up across this arterial plaque can translate into a net force that can dislodge the plaque from the arterial wall, causing it to move downstream and potentially causing an arterial blockage that would lead to a heart attack. So I think we've seen enough examples up to this point to see how this inverse relationship between fluid speed and fluid pressure can cause pressure gradients and net forces on objects in moving fluids. But we now want to be more quantitative in our use of Bernoulli's principle so that we can answer questions like how fast is a fluid moving in a given region, or what is the fluid pressure in a region where a fluid is in motion. In this slide, we will simply state what we call Bernoulli's equation, while in the next slides, we'll see where it comes from by actually deriving it. So Bernoulli's equation can be stated in a couple ways. Okay, we'll start a very general statement that looks like this, and we'll see what these terms mean, where, okay, P, this represents the pressure in a fluid, okay, plus this term 1/2 fluid density times fluid speed squared, plus this term rho gy, okay, fluid density times acceleration of gravity times y, which is a measure of height in a fluid, that the sum of these three terms must be equal to a constant. Now, what that constant is going to depend upon the problem. So a more useful form of this equation in problem solving is to actually compare these three terms at two different points in a fluid. Okay, since we know that the sum of these terms is a constant. So as we've learned in this entire field of fluid mechanics, there's no new physics here. All we've done thus far in talking about fluids is to apply the laws of mechanics that we already know about to the special case of fluids. Bernoulli's equation is nothing more than a statement of work energy conservation for fluids, as we'll soon discover. So in these next two slides, we'll apply the physics you already know to derive Bernoulli's equation. Ah, the fun of being in an engineering level physics course. So let's get started here. We'll start by considering the flow of an ideal fluid through a non-uniform pipe where a small volume of fluid, okay, that we will describe here in the lower section of the pipe having a cross-sectional area A1 and a length delta x1, where that small volume of fluid has been effectively transferred up to this higher portion in the pipe over here at position 2. We're going to start by calculating the net work done on this fluid. Now, if you think about it, okay, this fluid segment that we're considering in the lower portion of the pipe, what is making it move? Well, it's the fluid to the left of it in the pipe here that is not shown, that is exerting a force and pressure on it, that is doing work on it to make it move to the right. Likewise, this fluid up here in the higher portion, okay, that we are effectively moving from the lower portion to the higher portion, okay, this segment of fluid is also experiencing a force, but in this case a backward force and pressure from the fluid in the pipe to the right of it that we're not showing in the diagram. So the fluid to the right of it is effectively doing negative work on it, okay, exerting a force and pressure on it backwards, okay, as it moves forward in the pipe. So we can account for these two work terms here. We can say that the forward and backward pressures on the fluid, okay, do work on it as it moves from lower position 1 to a higher position 2. So here's an expression for the work that gets done on this fluid. Okay, notice here that F1 and F2, these are simply the forces due to fluid pressure. Okay, like we said, F1, that is the fluid to the left of it pushing the segment of fluid forward, and F2, the force due to fluid pressure on the right of the fluid in the upper segment, okay, pushing it backwards. Okay, evaluating the cosine 0, cosine 180 terms, okay, we end up with this expression, and then translating our force, okay, into a pressure times an area. This is the language of fluid mechanics here. We end up with this expression, okay, for net work. Now here you'll notice that, okay, A1 delta X1 here, as we see, represents the volume of fluid here. And A2 delta X2 here represents a volume of fluid here. Since we're considering an ideal fluid here, an incompressible fluid, we see that the fluid volume here in the lower position, at position 1, is exactly equal to the fluid volume in the higher position here, position 2, in which case delta V1 and delta V2 are the same, and we can simply express it as delta V. So here is our expression for the net work being done on that segment of fluid as it effectively moves from low position to high position, okay, due to the fluid in the pipe not shown, okay, the fluid to the left pushing it forward and the fluid to the right of it pushing it backwards. Next, we're going to calculate the change in kinetic energy for this segment of moving fluid. And this should look familiar to you here. Okay, 1/2 mass times fluid speed squared, our change in kinetic energy. We will translate that into the language of fluid mechanics by representing the mass of fluid in terms of the density and volume of fluid. So here we have our expression for the change in kinetic energy of the fluid as it moves from its low position, position 1, to its high position at position 2. All right, so in our previous slide, we calculated the net work done on this segment of fluid as it moves from a low position to high position. We've calculated the change in kinetic energy for the fluid. Okay, all we have left to do here is to calculate the change in gravitational potential energy of this fluid as it moves from low position 1 to high position 2. So, the change in gravitational potential energy of this fluid segment having a mass m is just given by m times the acceleration of gravity times the difference in fluid height. Okay, as you can see in the diagram here, the fluid starts out at a height, okay, y1 in relation to some reference height, and it ends up at a higher position at a height y2. Once again, we translate mass into the language of fluids by talking about it being a measure of the density times the volume. And here we have, therefore, an expression for the change in gravitational potential energy. So we have these three terms. All we have to do now is put it all together. Okay, the conservation of work energy theorem simply tells us that the net work done on a system, in this case the segment of fluid, is exactly equal to its change in kinetic energy plus its change in potential energy. For mechanical systems, the change in potential energy is simply, at least in this case, a change in gravitational potential energy only. So substituting in these three terms that we derived, we come up with Bernoulli's equation, which looks like this. Okay, the term on the left here, okay, this is simply the net work done on this segment of fluid. Okay, here, these two terms here on the right, the first two terms represent our change in kinetic energy, and this last term here simply represents the change in gravitational potential energy as the fluid moves from position 1 to position 2. We can make this look a little bit different here. Okay, notice that we have a delta V in every single term here, so we'll divide through by a delta V, which, as we would expect, makes sense. We should not expect that Bernoulli's equation in any way depends upon how much of a fluid we're talking about here. All right, and okay, finally, we'll write Bernoulli's equation in its useful problem-solving form, where we can compare 2 points in a fluid, okay, point 1 on the left-hand side of the equation to point 2 on the right-hand side of the equation. Note that these three terms all have units of pressure. They're all measures of pressure. And I just want to point out here, obviously the first term on each side, P, well, definitely that's a measure of fluid pressure. The second term here, though, it should look to you a little bit like a kinetic energy term, right? Okay, the difference is, but instead of being a 1/2 mass times speed squared, which gives us a measure of energy, it's a 1/2 density times speed squared, which gives us a measure of fluid pressure. And likewise, the last term here, okay, rho gy should give you an indication. It should look like a gravitational potential energy term. Once again, replacing mass, okay, mgy to give you a measure of energy with a rho gy to give you a measure of pressure. Let's now apply Bernoulli's principle to a couple of examples. We'll return to the case of the sclerotic artery that we looked at previously to get some quantitative information about these arterial plaques. So in this problem, we're told that blood having a given density flows through an artery which is obstructed with a plaque attached to the arterial wall. And that where this plaque exists, the cross-sectional area of the artery has been reduced to 1/5 of its normal cross-sectional area. The bottom surface of the plaque, we're told, okay, has a given surface area, and we're assuming that the top surfaces in the channels, okay, have about the same surface area. We're asked to calculate the net downward force acting on the plaque that tends to dislodge it. So Bernoulli's principle doesn't tell us about force directly, it tells us about pressure. But knowing what we know, okay, previously here, okay, from the example we looked at, we see that qualitatively speaking, because of the constriction in the artery, according to the equation of continuity, the blood speed is going to increase in the constricted region due to the decrease in cross-sectional area, and that increase in blood speed should cause a decrease in blood pressure there. Okay, compared to the region above the plaque over here at point 1 in the diagram, where there's virtually no fluid speed and a much higher fluid pressure. So we're going to make the assumption that the speed of the blood here at point 1 is about 0, since there's really nowhere for it to go. So let's get started here. To apply Bernoulli's principle, we need to know the fluid speed at the 2 points we choose. Okay, so we're going to choose point 1 here and point 2 when we apply Bernoulli's equation. But first, to get the fluid speed at point 2, we're going to use the equation of continuity, okay, at what I'll call point 0 over here in the healthy region of the artery to figure out that blood speed. So since we've done this previously, we'll do it very quickly here. Okay, and the healthy cross-section of the artery has 5 times the cross-sectional area as the obstructed portion. So when we find the fluid speed here in the constricted portion of the artery at position 2, okay, then that speed should be 5 times, okay, the speed in the healthy portion, which gives us a speed of, okay, about 25 centimeters per second or 2.5 meters per second. All right, so we're now in a position to apply Bernoulli's equation. And we're going to make the assumption that in comparing point 1 in the artery here to point 2, while there clearly is a difference in height, that difference in height amounts to maybe a couple millimeters. It's a very small difference, and in terms of this gravitational potential energy and pressure, it's a difference that is not worth investigating. Its contribution is insignificant. So we're going to consider these to be about the same heights. Now, clearly, if we were told that we're going to compare 2 regions in an artery, let's say between an artery in a person's head versus foot, then we are talking about a difference in height of a meter or more. In that case, we should take into account the differences in the gravitational potential energy. So here's an expression for Bernoulli's equation. Okay, we've solved it for the pressure difference here, because this pressure difference, remember, is going to give us a net downward force. It's going to dislodge that plaque. And we'll notice here that when we plug in the numbers here, okay, rho, the density of blood is given. We found out the blood speed at position 2 in the artery here, okay, from the equation of continuity to be 2.5 meters per second. Remember, we assumed that the speed of the blood here at position 1 is virtually 0. And given the fact that y1 is about equal to y2, there's no, these potential pressure turns turn to 0. We do the number crunching. We get a value of about 3,200 pascals. That is the pressure gradient, okay, that tends to push this plaque downwards into the artery. And if we want to find the net force, okay, then the net force is simply that pressure difference or pressure gradient times the area, which is given to us in the problem, okay, half a centimeter squared, which we'll convert over here to MKS units, gives us a value of about 0.16 newtons. Now, just to point out here, 0.16 newtons, that may seem relatively small to you, but remember that if I said the weight of a very tiny apple is about a newton, this is about the fifth of the weight of an apple, and we're talking about a very small system like an arterial plaque attached to a wall. That represents a fairly sizable force that can clearly dislodge that arterial plaque and, potentially cause a heart attack. So doing a problem like this, it kind of makes you want to go out and order a nice, juicy, fatty hamburger, doesn't it? So in this last example we'll look at, this is sometimes referred to as Torricelli's theorem. We will derive, it is a special case of Bernoulli's principle. And we will see that in the next slide, it is the physics behind how a siphon works. Okay, but starting in this problem, we're told that consider a 2-liter Coke bottle with a hole in the bottom. Okay, when the top cap is removed, okay, with that hole in the bottom, okay, which we are told here is 20 centimeters beneath the surface of the liquid here. Okay, that is going to cause, in this case, Coke to come out of the hole at a certain speed. So in this problem here, we are asked to find out what is the speed of the Coke emanating from that hole that is 20 centimeters beneath the surface of the fluid, okay, at least to start out the problem. So obviously as that fluid leaves, that 20 centimeters is going to get smaller in time, in which case the fluid speed will get smaller as well. We're really asked to find the fluid speed right at the start of the problem. So here's a case where we're going to apply Bernoulli's equation, and to apply Bernoulli's equation we need to choose those 2 points in our fluid where we evaluate these pressure terms. So we're going to consider the top surface of the fluid to be 1 point, and the bottom surface, which is where we're asked to find information, okay, that will be where the hole is. That will be the second point we choose. So here we're going to make the assumption that, okay, the fluid speed up at the top surface, okay, up here, is going to be virtually 0. Okay, notice we're not given a value for it in the problem, but you've probably seen the equivalent of this many times in your life, that over here we can say that the fluid speed is virtually 0 compared to the speed of the fluid where the hole is. It's an approximation we'll make. And when you solve Bernoulli principle problems, you very often have to be thinking to make approximations like this, especially when the information is not given in a problem. Is the fluid speed there exactly 0? No, but think about the fluid speed there compared to the fluid speed at the other point you choose, and we see that it's virtually insignificant. So we're going to choose the hole as the 0 point to measure our height. Okay, we will assume that at this hole here, that's height 0, and then at the top portion of the fluid, that is going to be at a height of 20 centimeters or 0.2 meters above, okay, our bottom point, our second point. So we're now in a position to apply Bernoulli's equation to find the speed of the fluid at the bottom point, at the hole. There's a statement of Bernoulli's equation. Notice instead of using 1s and 2s, I've substituted the subscripts T and B for bottom. This is always a good idea because when you're using subscripts that don't make a lot of sense for the problem, it's easy to get quantities confused. So my recommendation is always is try your best to choose subscripts that will help you remember. It's one less way you got to worry about making a mistake when you solve these problems. And here, when we evaluate the terms here, okay, notice that at the top surface of the fluid here, okay, the pressure, the external pressure is simply that of air above it. In other words, atmospheric pressure. Okay, so here at the top surface of the fluid, the Coke, okay, that external pressure is atmospheric pressure. Notice here where the hole is, that portion of the fluid also is exposed to the atmosphere. So the external pressure there, okay, is also simply atmospheric pressure. We already said that the fluid speed at the top here, the Coke is not moving there, so that's why we have the 0 here. When we put in this gravitational potential energy term, okay, Coke is about water. It's got some sugar in it. Its density is probably a little bit greater than 1,000, but not much. Okay, times G times the height we said was 0.2. Fluid speed at the bottom here, okay, this term 1/2 fluid density times fluid speed squared. That's what we're trying to find. That's our unknown in the problem. Okay, and then remember we said that the bottom of where the hole is, that's what we arbitrarily determined to be height 0, so there is no y value there. There's no height there. And when we do the number crunching, we solve for V2. Okay, we come up with I should say V bottom, we come up with this expression here, okay, that the speed there is simply equal to the square root of 2 times the acceleration of gravity, okay, times the difference in height, okay, which is 0.2 meters, gives us a fluid speed of 2 meters per second. So the square root of 2g height factor, that's what we call Torricelli's theorem. Right, and lastly, we'll see how Torricelli's theorem can be used to predict, okay, or explain the action of the siphon. So I'll start by asking the question, how does the physics change if we replace a fluid-filled bottle with a hole with, okay, a fluid-filled bottle with a hose such that, okay, the distance between the fluid surface and the hole would be the same as the distance between the fluid surface and the bottom of the fluid-filled hose. Well, what you would find if you apply Bernoulli's principle is that the physics would be identical. Okay, the physics would not change at all. In other words, the speed of the water that would emanate from the hole at the bottom of the bottle would be exactly the same as the speed of the water that would be coming from the bottom of the hose. Okay, in this sense here, we see this is how a siphon works. You can actually get water to flow, in this case here, or appear to flow uphill, okay, through the hose, so long as the bottom of the hose is at a lower position, okay, than the other end of the hose. So in this little simulation here, we'll see how you can actually get water to actually flow uphill in the action of a siphon.